Hello and welcome to Late Night Space. Before we settle in, if you enjoy what you hear tonight, a like or a subscribe goes a long way. It helps other late night wanderers find this place, and honestly, it means a lot knowing someone out there is listening. And if you feel like it, leave a comment and let us know what's keeping you up tonight. Whatever brought you here, you're in the right place. This channel is for those in between hours, the ones where everything finally goes still, but your brain doesn't. So tonight, instead of staying stuck in your own head, let's look up, way up. Just beyond the thin layer of air wrapped around this planet, space begins. Not with a bang or a clear border, it just gradually fades. Fewer molecules, more distance. The sounds you're used to get thinner and thinner until there's nothing left. In the movies, space is loud. Things explode, engines scream, stars hum with energy. But that's not how it actually works. Real space is quiet, almost perfectly quiet. So as this plays, picture yourself drifting upward, past rooftops, past clouds, past the satellites blinking silently in orbit. The Earth falls away, the air thins out, and then nothing. No sound at all, just motion, light, and distances so large they stop making sense. But quiet doesn't mean empty. Stars are burning right now. Planets are in motion. Entire galaxies are slowly pulling apart from one another. It's all happening. It just doesn't make a sound. The universe doesn't announce itself. It's simply there. This is late night space. A place to breathe a little slower, let your mind drift, and sit with how strangely peaceful it feels to think about something that big. Tonight, while the world around you sleeps, we're starting with a simple question. Why is space so quiet? The silence begins sooner than most people expect. Long before the stars feel close, long before Earth looks small, sound is already weakening. Even now, wherever you are listening from, sound depends on an invisible crowd of particles pressing gently against one another. Every word, every tiny creak of a building settling, every soft breath in a quiet room exists because air is there to carry it. Picture the place you are in right now as a little pocket of moving molecules. Air does not feel like much, but it is busy. It presses against skin, it fills lungs, it cushions everything. It is the reason a whisper can cross a room, and the reason a distant car can reach you as a faint, rolling hush. Sound is not a decoration added to reality. It is reality jostling itself and passing that jostle along. Now imagine lifting gently upward. Not in a rocket, not with alarms and shaking bolts, just a slow drift, like a balloon that does not stop rising. At first, nothing seems different. The sounds of Earth still cling to you. But altitude has a way of changing the rules one small step at a time. As you climb, the air becomes thinner. That does not mean it vanishes. It means the same space contains fewer particles. The crowd grows sparse. The invisible hands that carry vibrations from one place to the next are no longer packed shoulder to shoulder. Sound still exists, but it has a harder time staying coherent. It loses strength more quickly. It feels less certain. This is one reason aircraft cabins are pressurized. Human bodies are built for dense air. Ears are built for it too. They rely on pressure differences to translate vibrations into perception. High above the ground, outside the cabin, the air is too thin to breathe comfortably, and it is also too thin to support sound in the way you are used to. If you could stand there safely, you would not hear the world below the way you expect. The Earth would still be busy, But the sound would not make the trip. Keep drifting higher. Below you, the atmosphere stretches like a delicate skin around the planet, thicker near the surface and fading steadily with height. There is no sharp edge where air ends and space begins. There is only a slow transition where the chance of one molecule bumping into another becomes less and less likely. Down on the surface, air molecules collide constantly. They are close enough to share motion immediately. Up here, collisions become rarer. A vibration that would have been carried smoothly through dense air starts to fall apart. It is like trying to pass a message through a crowded room where everyone is holding hands, compared to trying the same thing in a wide field where people are standing far apart and looking in different directions. The quiet you are moving toward is not a special property of the universe. It is simply what happens when there is no longer a continuous chain of matter to pass vibrations along. And the strange part is that the transition can feel so ordinary. The sky looks much the same, just darker and deeper. Earth still curves beneath you. Sunlight still falls across the planet in a slow sweep. Weather still moves in soft spirals. Cities still glow faintly as scattered constellations of their own. There is motion everywhere, but sound is already slipping away. At a certain height, if you could open a window, you would not hear a dramatic fade into a hush. You would experience something more abrupt than that. Sound would not travel out into the thinning air in any meaningful way. Your voice would not go anywhere. It would not become quieter at a distance. It would simply fail to form a traveling wave in the first place, because the medium around you would not cooperate. Inside a sealed cabin, sound continues as normal. Inside a spacecraft, the same. Fans spin. Systems hum. Tools clink. Astronauts speak to each other. That is not because space is secretly full of sound and people just do not notice. It is because the sound is happening inside a manufactured bubble of air, surrounded by walls that keep the medium in place. Sound belongs to the bubble. Space outside does not participate. Now imagine the bubble is gone. Not the spacecraft, not the suit, just the idea of a local pocket where air has been brought along. Outside, sound has no place to live. There is no atmosphere waiting to carry it. The quiet is not a muffling blanket. It is an absence of the very thing sound needs to exist. This is where a common misunderstanding sneaks in. Silence feels like a lack of activity. On Earth, if a room goes silent, it often means something has stopped. A machine turned off, a crowd dispersed, a storm passed. In human life, silence is frequently a consequence. In space, silence is a condition. Stars burn, magnetic fields twist, radiation streams outward, dust drifts, planets fall and swing through gravitational arcs, asteroids tumble, comets shed gas and grit. None of that requires sound, and none of it produces sound that can travel through the surrounding vacuum. The universe is active, but it is not acoustically social. Even events that feel like they should be loud are quiet. A violent explosion can occur, releasing tremendous energy and hurling material outward at extraordinary speeds, and it will still not produce sound that travels through the emptiness. There can be a shock wave within the expanding cloud of debris because there is matter there, at least for a while, but beyond that cloud, there is no continuous medium, no chain, no crowd, no passing along of pressure. The sound has nowhere to go. The farther you drift from Earth, the more this truth settles in. Sound is not missing because the universe forgot to install it. Sound is missing because sound is something that happens only when matter is close enough to share motion. And this is the first key step toward answering the question. Space is quiet, not because it is empty in the absolute sense, but because it is empty enough that sound cannot survive. Let the silence sit for a moment, not as emptiness but as distance, not as absence but as separation. The universe is not trying to be eerie, it is simply very, very spread out. From here, the next step is to look more closely at the thing that is failing. Because once sound is understood clearly, the silence stops being surprising. It becomes inevitable. Sound begins with motion, not the motion of a person walking across a room, but the motion of particles in place, pushing and pulling on their neighbors. When a guitar string vibrates, it does not send tiny pieces of string flying outward into the air. It moves back and forth, and in doing so, it squeezes the nearby air, then relaxes it, then squeezes it again. That squeezing and relaxing creates regions of slightly higher pressure and slightly lower pressure that move outward as a wave. A human voice works the same way. Vocal cords vibrate. Those vibrations press into the air in the throat and mouth, shaping it into patterns that become speech. A speaker cone moves back and forth. A drum skin flexes. A door slams, momentarily compressing the air in front of it. In every case, the sound is not an object launched into space. It is a pattern of pressure moving through a medium. That medium can be air, water, or solid material. It can be anything made of particles that can interact strongly enough to pass the motion along. The crucial requirement is that the particles must be close enough to affect one another in a continuous way. In air near the ground, particles are packed densely enough that each one collides with others constantly. In that environment, a pressure change spreads outward smoothly. The wave is not carried by any single molecule traveling all the way from the source to your ear. Instead, the wave moves because each molecule nudges its neighbor, which nudges the next, like a stadium wave made of microscopic contact. This is why sound can travel through a wall. The wall is solid, with particles bound closely together. Vibrations can pass through it efficiently. In many cases, sound moves faster in solids than in air, because the particles are tightly linked and transmit motion quickly. In water, sound also travels well, because water molecules are closer together than air molecules, giving the wave a stronger and more continuous path. In gases, the situation is looser. Particles are farther apart. Collisions still happen, but the chain is less stiff, and sound tends to travel more slowly than it does in solids. Yet at sea level, it is still dense enough to do the job. Now take that gas and start removing particles, not by a small fraction, but by enormous degrees. Spread the remaining molecules through an expanding volume. Increase the average distance between collisions. Make it so a molecule can travel a long way before encountering another. At some point, the idea of a smooth pressure wave stops making sense. There is no longer a continuous medium. There are particles, yes, but they are not cooperating as a crowd. They are isolated travelers. In that situation, you might still have motion and you might still have impacts, but you do not have a wave that propagates with the familiar behavior of sound. The vibration cannot hand itself off cleanly. It cannot maintain its identity across distance. It cannot reach an ear. This is why the silence of space is not a kind of muffling. It is not as if sound tries its best and then gets absorbed. Sound fails at the starting line because the requirements for sound are not met. Scientists have understood pieces of this for a long time, though the path to modern understanding was gradual. Galileo Galilei explored vibrations and the relationship between physical motion and what people perceive as pitch. Over time, the concept of sound as a wave became clearer, and Isaac Newton worked on describing sound in terms of mechanical processes in air. Later, scientists refined the picture by understanding how pressure, density, and temperature influence the speed of sound in a medium. The details can become technical, but the underlying idea remains gentle and simple. Sound is a traveling pattern of compression and expansion. It is matter communicating motion through contact. This also explains a subtle point that can be oddly comforting. Silence in space does not mean nothing can travel. Plenty can travel. Light travels because light is an electromagnetic wave. It does not require a medium in the same way sound does. Radio waves travel. Infrared radiation travels. Visible light travels. X-rays travel. The universe is full of signals, and space is an excellent place for them to cross long distances without being blocked by dense material. So if the universe seems silent, it is not because it is cut off. It is because it speaks in forms other than sound. This is why astronomy is possible at all. The most distant galaxies send light across billions of years of travel. Pulsars, which are rapidly rotating neutron stars, send regular flashes like cosmic lighthouses. The sun floods the solar system with light and streams of charged particles. Space is not mute, it is simply not audible. Even the idea of a cosmic event being loud depends on a human habit of translating energy into sound. On Earth, large releases of energy often occur in air, and the air obligingly turns that energy into pressure waves that reach your body. A thunderclap, for example, is not sound produced directly by lightning as a separate substance. It is the air expanding rapidly due to heating, creating a shock wave that becomes the sound you hear. Without air, the lightning would still exist as an electrical event, and it would still produce light, but there would be no thunder. This is the same principle scaled up to the cosmos. A supernova releases extraordinary energy. It throws matter outward at tremendous speeds. It fills space with radiation. It can even create shock waves inside the expanding material, where there is gas and plasma to support them. But outside that material, the shock does not travel as sound because there is no surrounding atmosphere to carry it. Once this is understood, the silence begins to feel less like a spooky feature and more like a logical outcome of emptiness and distance. Sound is an intimate phenomenon. It requires closeness. It thrives in crowded environments. Space, by its nature, is the opposite. It is defined by separations so large that even the smallest interactions become rare. And this is where a gentle reframing can settle the mind. The quiet of space is not a warning sign. It is a measurement. It is what the universe looks like when matter is spread thin and motion is allowed to unfold without the constant companionship of air. So when you picture yourself drifting beyond Earth, hearing nothing, it is not because the universe has gone still. It is because you have stepped beyond the conditions that make sound possible. And from that starting point, the journey outward becomes clearer. The deeper you move into space, the less the universe behaves like a room, and the more it behaves like a vast distance filled with light, particles, gravity, and time. The silence is not emptiness. It is scale made audible only by its absence. The feeling of leaving Earth is often imagined as a single dramatic moment, like stepping over a threshold. But the planet does not really offer thresholds. It offers gradients, a slow thinning, a long, patient fade. The air that cradles every sound is not one uniform blanket. It is layered, each layer with its own character, its own chemistry, its own quiet physics. Close to the ground is the troposphere, the layer that holds almost all familiar weather. This is where clouds form, where storms swell, where sea level pressure makes life feel normal, and voices behave themselves. In the troposphere, air is dense enough that sound can spread easily, bounce off surfaces, and travel through streets and rooms as if it belongs there, because it does. Above that is the stratosphere, calmer in some ways and strangely ordered. It contains the ozone layer, which plays a crucial role in absorbing much of the sun's ultraviolet radiation. The stratosphere is also where high-altitude aircraft sometimes cruise, and where the sky darkens into a deeper blue. Sound still exists here, but the environment is shifting. The air is thinner, and vibrations lose their confidence. They can still travel, but the rules are beginning to loosen. Higher still is the mesosphere, where the air becomes so thin that it barely feels like a place at all. This is where many meteors burn up, turning into brief streaks of light as they meet the few molecules that remain. The idea of sound up here becomes increasingly strange. There are molecules, yes, but they are spaced out. Collisions are less frequent. The medium is no longer a reliable partner. Then comes the thermosphere, a layer that can become extremely hot in terms of particle energy, even while it feels nothing like heat to a human body. This is an important distinction. Temperature in physics is tied to the average kinetic energy of particles. In the thermosphere, particles can be energetic, but there are so few of them that they do not carry heat the way dense air does near the surface. If you were there, the words hot and cold would both start to feel inadequate. It is a realm where intuition needs a gentle recalibration. Beyond that, the atmosphere fades into the exosphere, where individual particles can travel long distances without meeting a neighbor. This is where the air truly begins to stop behaving like air. The concept of a wind loses meaning. The concept of a pressure wave becomes almost impossible. There is still matter, still motion, still interaction, but it is no longer the crowded environment sound requires. Some people point to a particular altitude as the start of space, often referencing a boundary used for practical purposes, such as the Kármán line, which sits at about 100 kilometers above sea level. It is a useful line in engineering and aviation, but it is not a wall. The planet does not care about labels. The transition is real, but it is smooth. And because the transition is smooth, the silence does not arrive as a single dramatic hush. It arrives as a steady loss of the conditions that allow sound to exist. There are real experiments that make this feel less abstract. High-altitude balloons launched by research teams and space agencies rise into the upper atmosphere carrying instruments to study pressure, temperature, radiation, and particle density. NASA has used balloon missions for decades, and similar work is done by organizations across the world, including the European Space Agency and national research institutions. These balloons do not just float into darkness for the romance of it. They measure the slow fading of the atmosphere in numbers, confirming what the body would feel if it could go there safely. As those balloons rise, one of the most striking shifts is how sound would behave around them. At ground level, a balloon is a noisy object if you stand close enough. Fabric creaks, equipment vibrates, air moves around it in ripples. But higher up, even if the balloon itself continues to jostle and flex, there is less and less medium to pass those vibrations outward. The environment becomes less like a room and more like an open, thinning expanse. Another kind of mission, the sounding rocket, briefly crosses these regions to take measurements before falling back. The name contains the word sound, but not because the rocket is listening for noise in the way people usually imagine. Sounding refers to probing, like taking the measure of a place that is difficult to reach. Still, there is something quietly funny about a sounding rocket flying into a region where sound itself starts to fail. It is like sending a message in a bottle to a place where bottles have not been invented. All of this builds toward a simple truth. Earth is not the natural home of silence. Earth is the natural home of sound. Sound is abundant here because matter is abundant. As you leave, the atmosphere does not stop suddenly. It simply thins until it can no longer support the one thing your ears are built to track. And now, the shift becomes especially important. Because when people say space is silent, they often imagine space as one uniform emptiness. But near Earth, space is not the deep, ancient quiet between galaxies. Near Earth, space is a busy neighborhood. It is filled with human artifacts, drifting technology, and fragile habitats that carry small pockets of air like life rafts. Low Earth orbit is where many satellites circle the planet. It is also where the International Space Station travels, moving at roughly the speed of a rifle bullet and completing an orbit about every 90 minutes. The speed is enormous, yet the surrounding environment remains nearly silent. That contrast is one of the strangest features of spaceflight. Tremendous motion, almost no sound. Inside the International Space Station, there is plenty of noise. Not the inspiring kind, not the cinematic kind, but the practical hum of life support systems, ventilation fans, pumps, computers, and circulating air. The station is a sealed environment, and it must keep moving air to keep carbon dioxide from pooling and to keep temperature stable. Astronauts sometimes describe the interior as constantly humming, like living inside a machine that never truly sleeps. That sound is not a bonus feature. It is the signature of survival. Yet just outside the station's walls, none of it carries outward. There is no surrounding atmosphere to pick up the vibrations and spread them. The station can be roaring inside and perfectly silent outside at the same time. The same is true of astronauts on spacewalks. In a spacesuit, there is a helmet filled with air, and there are structures that can transmit vibrations through solid material. An astronaut may hear the faint vibration of life support, the whisper of airflow, the sound of a radio speaker inside the suit. They may also hear something through bone conduction, where vibrations travel through the body rather than through air. But if a tool is dropped, if a panel flexes, if a jet of gas spurts into the vacuum, the sound does not travel outward as sound. It does not have a medium to convert that motion into a pressure wave that can carry across distance. This is one of the most important clarifications for understanding the silence of space. Silence does not mean nothing is happening. It means that happening is not being translated into pressure waves in an open environment. Spaceflight history offers plenty of moments where this becomes vivid. During the Apollo missions, astronauts walked on the moon in suits filled with air, speaking to each other through radios. The moon has an extremely tenuous atmosphere, so there is effectively no sound outside a sealed system. A hammer striking a surface on the moon does create vibrations in the hammer and in the ground, and those vibrations can be felt through contact. But there is no air to carry a clang outward into the landscape. The sound does not spread. It stays local, trapped inside materials, not drifting freely through space. That difference between local vibration and traveling sound is why the popular idea of loud space battles is so misleading. It is not that filmmakers are unaware of the science. Often, they know perfectly well. It is just that silence on screen can feel emotionally empty, and the human brain expects impact to come with sound. A silent explosion looks wrong to us, even if it is closer to reality. The universe is not obligated to match our expectations, but storytelling often is. In real physics, if an explosion occurs in a vacuum, there may be a flash of light. There may be a burst of expanding debris. There may be intense heat radiating outward. There may be a cloud of fast-moving particles and gas within which pressure waves can briefly exist. But once that expanding material spreads out, the conditions for sound vanish. There is no surrounding air to carry an ongoing boom across space. The loudness people expect is largely an Earth habit, because on Earth the air eagerly turns rapid expansion into a pressure wave that reaches ears, windows, and walls. Near-Earth space is also filled with another kind of quiet activity that can be easy to overlook. Invisible radiation moves through it constantly. Charged particles from the sun, known as the solar wind, sweep past. Earth's magnetic field guides many of those particles towards the poles, contributing to auroras. Satellites navigate this environment with careful shielding and precision. Organizations such as NASA, the European Space Agency, and the National Oceanic and Atmospheric Administration monitor aspects of this space weather, because it can affect communications, navigation systems, and power grids. All of this is happening in a region that remains acoustically silent. There is motion, there is energy, there's interaction, there is even danger in the form of radiation and high-speed debris. But there is no soundscape, no background roar, no cosmic wind in the ears. And this is where the quiet begins to take on a different meaning. Silence stops being an absence and becomes a signpost. It tells you something precise about the environment. It tells you there is not enough matter here for vibrations to link arms and travel. It tells you that the universe, at least in this region, is dominated by separation. That separation grows even more pronounced as you move away from Earth and into the wider solar system. The silence is not a single phenomenon. It deepens in layers, just as the atmosphere fades in layers. And with that, the mind is ready to move outward again, past the busy neighborhood of low Earth orbit, toward regions where even human machinery becomes rare, and where the thin traces of matter become thinner still. Leaving low Earth orbit is like leaving a city at night. At first, there are still lights behind you. There are still signs of presence. Even as the darkness deepens, you can look back and see that something busy exists somewhere. But the further you drift, the more the universe stops feeling like a place built for visitors and starts feeling like what it has always been, whether anyone is watching or not. One of the most important words in this story is vacuum. It is often used as a synonym for emptiness, and in everyday speech that makes sense. A vacuum cleaner removes air from a small space. A sealed container can be pumped down until the pressure is extremely low. The word carries the idea of nothingness. But in space science, vacuum is not nothingness. Vacuum is a measure of scarcity. A perfect vacuum, in the sense of absolute zero particles, is not something the natural universe offers very easily. Space is not filled with air, but it is filled with traces. A few atoms here, a few molecules there. Dust grains drifting in long arcs. Charged particles moving under the influence of magnetic fields. Photons crossing distances without caring what they pass through. So it helps to be precise. When space is described as a vacuum, it is describing an environment where the density of matter is so low that familiar processes begin to fail. Sound is one of the first processes to fail because sound depends on continuous particle-to-particle interaction. But other things fail too, in different ways and with different thresholds. Even close to Earth, the environment is thin, but the solar system is not a clean, empty stage. It has structure, it has debris, it has a faint, restless flow from the sun that fills the space between planets. Interplanetary space is often described as a near vacuum, and it is, but it is not silent because it is absolutely empty. It is silent because it is empty enough. To feel the difference, imagine a room filled with people standing shoulder to shoulder. A tap on one person's shoulder can be passed along quickly. The crowd transmits the motion. Now imagine the same room with only a handful of people standing far apart. A tap no longer spreads. It stays with the person who received it. There is no chain, no shared wave. That is what a vacuum does to sound. It breaks the chain. There are places in the universe where gas is dense enough to support sound, such as inside stars within thick planetary atmospheres, or inside gas clouds where particles are close enough to behave like a fluid. But the vast majority of the space between those places is too thin. The particles do not form a continuous medium. They are not a fluid. They are a sparse population. This is why a vacuum is not a void of action. It is an environment where action takes different forms. In laboratories on Earth, researchers create high vacuum environments to study physics under controlled scarcity. Large particle physics facilities such as CERN rely on vacuum systems to guide particle beams through long tunnels with minimal interference. The purpose is not to create nothingness, but to remove enough matter that particles can travel without being scattered constantly by stray molecules. These engineered vacuums provide a helpful analogy to space, not identical, but conceptually useful. They demonstrate that a vacuum is not a magical absence, but a reduction of interactions. This matters because the common picture of space as a kind of empty container can lead to mistaken ideas. It can make silence feel like an eerie property of emptiness itself. But the more accurate picture is simpler. Space is quiet because it is dilute. It is quiet because matter is spread out so thinly that sound waves cannot move through it as a wave. Even when there are particles, they are often too far apart. In the region between Earth and the Moon, and between Earth and the Sun, the average distance between particles can be immense compared to the distances involved in ordinary sound propagation. A sound wave in air is a coordinated ripple of pressure changes. It requires constant neighbor-to-neighbor transfer. In a sparse medium, the ripple cannot stay coordinated. This becomes even clearer when thinking about what sound is at the microscopic level. A sound wave is not a single particle traveling outward. It is a pattern of compressions and rarefactions. Those patterns require enough particles close enough together to form a continuous pressure field. In a vacuum, the idea of a continuous pressure field breaks down. So space is not silent in the sense of having no energy. It is silent in the sense of not allowing pressure waves to travel freely. Once that distinction settles in, the solar system begins to look different. It becomes a place where silence is normal, but not because nothing is there. It is normal because what is there is too thin to cooperate. Now the focus can drift into the region most people imagine when they picture the solar system: the space between planets, the long arcs of orbits, the vast gaps that feel empty at human scale, even though they contain a faint, constant stream from the sun. Interplanetary space is shaped by the solar wind, a flow of charged particles that streams outward from the sun in all directions. It is mostly made of electrons and protons, and it travels at speeds of hundreds of kilometers per second, which is a scale that belongs to astrophysics rather than daily life. This solar wind is not a gentle breeze. It is a plasma, a charged gas, carrying energy and magnetic fields outward across the solar system. This is where language can become misleading again. Words like wind make people imagine a sound. On Earth, wind is noisy because it moves through dense air, creating turbulence that the ear interprets as rushing, whistling, or roaring. In space, the solar wind is not a sound-making wind. It is a silent flow of particles, too thin to carry audible pressure waves. Yet the solar wind is real, measurable, and powerful in its own way. It shapes comet tails, pushing gas and dust so that comet tails point away from the sun. It influences planetary magnetospheres, including Earth's, compressing the magnetic field on the sun-facing side and stretching it into a long tail on the night side. It can create geomagnetic storms that disturb satellite electronics and power systems back on Earth. NASA has studied the solar wind for decades, and missions such as the Parker Solar Probe have flown closer to the sun than any spacecraft before, measuring the solar corona and the behavior of particles streaming outward. The European Space Agency has also contributed major missions, including Solar Orbiter, which observes the sun and its effects on the surrounding space environment. These missions reveal a solar system that is not empty, but actively shaped by flows and fields. Still, none of this produces a soundscape in the way humans expect. If you were floating between Earth and Mars, the solar wind would pass through you and around you silently. It would not whistle, it would not howl, it would not roar. You would see sunlight. You might see planets as bright points. You might see dust caught in the light. But your ears would have nothing to do. Even the planets themselves do not create sound in the space between them. A planet can have a thick atmosphere full of winds and storms, and it can be loud within that atmosphere, in its own way. Venus has a dense atmosphere. Jupiter has powerful storms. Saturn's atmosphere churns. Mars has thin winds and dust storms. But their sounds, whatever they would be if you were inside their atmospheres, do not leak out into interplanetary space. The silence returns immediately outside the atmospheric boundary because there is no medium to carry those pressure waves away. This is why the solar system can feel so peaceful in a way, that is almost abstract. There is motion everywhere, but it is clean motion. Objects move along gravitational paths with little friction. Spacecraft travel long distances without needing to push against air. Orbits are quiet, not because they are gentle, but because there is almost nothing to rub against. Even impacts, which can be violent, do not create traveling sound through the vacuum. An asteroid striking the moon creates seismic waves in the moon itself, vibrations that can ring through rock for a long time. Instruments left on the moon by Apollo astronauts detected these moonquakes and showed that the moon can ring like a bell after an impact. But the sound stays in the rock. It does not become an audible boom traveling through the space above the surface because there is no air to turn vibration into sound. This reveals a more subtle kind of quiet. Space allows motion to happen without the constant conversion of energy into noise. On Earth, much of what is loud because energy is being dissipated through air, through friction, through turbulence. In space, energy can remain in motion, in orbit, in heat radiation, in electromagnetic signals, without ever becoming sound. So interplanetary space is not an empty void. It is a thin environment filled with particles, fields, sunlight, and long trajectories. It is shaped by the sun's influence and by the gravity of planets. It contains the invisible breath of the sun moving outward, and it contains the small debris left behind from the formation of the solar system. And yet, it remains quiet, because quiet is what happens when matter is spread out, when the chain of contact is broken, and when sound waves cannot find enough neighbors to become a wave. As you drift farther out, the distances increase again. The particles grow sparser. The influence of planets becomes smaller. The sun becomes a bright star rather than a dominating presence. The solar system begins to feel like one local bubble in a much larger darkness. And beyond that, the silence deepens into the space between stars. Beyond the solar system, the quiet takes on a new quality. Between planets, there is still a sense of being inside a neighborhood. The sun is bright and close. The solar wind is present, flowing outward like a steady, invisible tide. Even when it cannot be heard, it still shapes the space around it, giving the whole region a kind of structure. But as you drift farther, that structure loosens. The solar wind becomes weaker with distance, not because the sun stops, but because the same stream is spread across an ever-expanding sphere. The particles are still there, still moving fast, still carrying magnetic fields, but they become more diluted, less frequent. The sun is still the loudest thing in the sky visually, but its reach as a physical environment slowly fades. At the outer edges of the solar system, something like a boundary begins to form. Not a wall and not a line you could see, but a place where the outward push of the solar wind starts to meet the surrounding material of interstellar space. That surrounding material is thin, but it is not absent. It presses back. Scientists describe this outer bubble around the sun as the heliosphere. It is the region where the solar wind dominates, like a protective influence that carves out a cavity in the larger interstellar medium. The interstellar medium is the faint mixture of gas and dust that fills the space between stars. It is not dense like air. It is more like a whisper of matter scattered through vast distances. Yet even that whisper has enough presence to shape where the sun's influence finally begins to give way. Spacecraft have actually reached this region. The Voyager missions, built and launched by NASA, traveled outward for decades, carrying instruments that measured particles and fields as they moved away from the Sun. Voyager 1 and Voyager 2 did not sail into a cinematic emptiness. They crossed into an environment that is still almost unimaginably sparse, but measurably different. There is a region called the heliopause, where the outward flow of the solar wind is finally balanced by the pressure of the interstellar medium. Beyond that, the solar wind no longer defines the local environment. The spacecraft are still moving, still transmitting faint signals back to Earth, but the space around them is now governed more by the galaxy than by the Sun. It is tempting to imagine that crossing into interstellar space would suddenly make everything feel more dramatic. But from the perspective of sound, nothing changes in a way your ears could notice. It was already silent. It remains silent. The difference is in density, composition, and the dominant sources of particles and fields. One way to picture interstellar space is to imagine an ocean that is so thin it is almost not an ocean at all. It has currents, but the currents are slow and vast. It has clouds, but the clouds are made of gas so tenuous that the word cloud starts to feel like a metaphor. It has dust, but the dust grains are small and far apart, drifting in the dark, like isolated seeds. Even so, this environment is crucial. The interstellar medium is where stars are born and where they return material when they die. It is the substance that connects star systems across a galaxy. It is thin, yes, but it is not meaningless. In some regions, the interstellar medium is mostly hydrogen, the simplest and most abundant element in the universe. In other regions, there is helium and traces of heavier elements such as carbon, oxygen, nitrogen, and iron, often created in stars and dispersed by stellar winds and supernova explosions. The astrophysicist Cecilia Payne-Gaposchkin played an important role in establishing that stars are primarily made of hydrogen and helium, which helped reshape how scientists think about what fills the space between them as well. Interstellar space is not uniform. There are cold, dense molecular clouds where particles are close enough to form molecules, including molecular hydrogen. These clouds can be the birthplaces of new stars, collapsing under gravity until nuclear fusion ignites in a new stellar core. There are also hot, ionized regions where ultraviolet radiation has stripped electrons from atoms, turning the gas into plasma. And there are warmer, more diffuse regions, including the kind of interstellar environment the solar system is currently moving through, often called the local interstellar cloud. Even in the denser parts of the interstellar medium, the density is still extremely low compared to Earth's atmosphere. The difference is not subtle. Earth's air is a crowded ballroom. Interstellar space is a continent with a few scattered hikers. A sound wave cannot form the way it does in air, because there is no continuous pressure field to carry it. The particles are too far apart to act like a shared medium for audible vibrations. And yet, the interstellar medium does support other kinds of waves. Magnetohydrodynamic waves, for example, can travel through plasma, shaped by magnetic fields and charged particles. These are not sounds you could hear, but they are real physical disturbances, and they matter for how energy moves through space. Space remains quiet to human hearing, but it is not static. It has its own forms of motion and communication. This is part of what makes the silence so profound. The universe is full of signals, but most of them are not meant for ears. They are meant for instruments. Radio telescopes, space probes, spectrometers magnetometers. The language of space is electromagnetic radiation, particle streams, gravitational influence, and slow dynamical change. And as you drift among the stars, the scale becomes more personal in a strange way. The nearest star systems are still separated by distances so vast that even light takes years to cross them. If you imagine traveling from the Sun to the nearest star, the distance is not something a mind holds naturally. The space between is not a corridor, it is an expanse. A long, emptying stretch where the interstellar medium is the only faint companion. In that emptiness, the silence is complete, not because nothing exists, but because nothing is close enough to pass a vibration along. Now, as the view widens, the stars begin to stop feeling like isolated lamps scattered on a black ceiling. They begin to feel like part of a structure. That structure is a galaxy. A galaxy is not just a collection of stars, it is an ecosystem of stars, gas, dust, and dark matter bound together by gravity. The Milky Way, the galaxy Earth belongs to, is a barred spiral galaxy with a dense central bulge and spiral arms where star formation tends to be more active. The Sun sits in one of the calmer regions of the disk, not in the crowded center, but not in the empty outskirts either. Inside a galaxy, there is motion on every scale. Stars orbit the galactic center. Gas clouds drift and shear. Spiral arms act like patterns in the disk, regions where density waves compress gas and encourage new star formation. Supernovae erupt, enriching the surrounding medium and pushing shock fronts through gas clouds, sometimes triggering new collapses, sometimes dispersing material into thinner regions. If any of this happened in air, it would be unimaginably loud. But a galaxy does not provide air. It provides emptiness, punctuated by islands of matter. This is where the silence can feel almost paradoxical. A galaxy is busy. It is alive with physics. Yet the space between the stars remains so thin that most of the action cannot become audible sound. Even within galaxies, there are environments where gas is dense enough for pressure waves to exist in a local sense, such as within molecular clouds or within accretion disks around compact objects. But the galaxy as a whole is not filled with a continuous medium the way a planet's atmosphere is. A sound wave cannot travel freely across the spiral arms. It cannot cross the voids between star systems as an audible ripple. The distances swallow it. Galaxies also include a mystery that has shaped modern astrophysics. When astronomers began measuring how stars orbit within galaxies, the observed speeds did not match what would be expected if only visible matter were present. Vera Rubin's work on galaxy rotation curves provided strong evidence that galaxies contain far more mass than can be seen directly, helping support the case for dark matter as a dominant component of galactic structure. Earlier, Fritz Zwicky had also inferred missing mass in galaxy clusters. These ideas were not built from intuition. They were built from careful observation of motion in a universe that, to the ear, remains silent. Modern observatories continue to map this silent motion. The European Space Agency's Gaia mission measures the positions and motions of stars in the Milky Way with extraordinary precision, revealing the galaxy as a dynamic system, full of streams, clusters, and subtle gravitational influences. Radio observatories such as the Atacama Large Millimeter Array trace cold gas and dust, showing where stars are being born. Space telescopes such as the Hubble Space Telescope and the James Webb Space Telescope observe galaxies across deep time, capturing light that has traveled for billions of years. All of these instruments are listening, in a sense, but not with ears. They are gathering signals that travel through the vacuum without needing a medium. They are reading the universe through light, through radio waves, through infrared radiation, through the faint signatures of elements in starlight. And this is the calm twist at the heart of the silence. The universe is quiet, but it is not hidden. It is quiet because sound is a local phenomenon, dependent on crowded matter. But the universe is visible, measurable, and richly communicative through other channels. As you drift through the galaxy in your imagination, the silence remains absolute, yet the scene is full of structure. Stars are not randomly scattered. They belong to spiral arms and star clusters. Gas and dust form filaments and clouds. The galactic center holds a supermassive black hole, a region of intense gravity and energetic processes, still silent to the ear outside its immediate environment, but brilliant in electromagnetic signals. And beyond the Milky Way, there are other galaxies, separated by even greater emptiness. The silence is not a void in the story. It is the background condition that makes the scale of the universe feel real. From here, the next widening step is inevitable. If the space between stars feels empty, and the space between galaxies is even emptier, then the quiet is not just a feature of the solar system or the Milky Way. It is a feature of the cosmos itself, deepening as distances grow beyond anything a single galaxy can contain. Beyond the Milky Way, emptiness becomes more than a background. It becomes architecture. Galaxies gather in groups and clusters, bound together by gravity like slow, ancient communities. Those clusters connect into larger arrangements, long chains and sheets that stretch across space. And between those chains, there are enormous regions with very little inside them at all. These are cosmic voids. The word void sounds absolute, like a perfect nothing. But in cosmology, a void is more like a thin place in the universe, a region where matter is simply less concentrated than average. There are still particles. There is still dark matter. There is still light crossing through. But compared to the crowded filaments of galaxies, a void is an immense quiet gap. To picture it, imagine a night sky filled with scattered lanterns. Up close, the lanterns look randomly placed. Step back far enough, and patterns appear. Some regions hold many lights. Some hold almost none. The darker regions are not empty in an absolute sense. They are just underfilled. Cosmic voids can be staggeringly large. They can span distances so vast that the mind starts to lose its grip on what size even means. These regions exist not because something scooped matter out of the universe, but because gravity gathered matter elsewhere. Over billions of years, slight variations in the early universe grew into structure. Dense regions pulled in more material and became denser still, while less dense regions became emptier by comparison, like valleys deepening as mountains rise. This large-scale structure did not appear by guesswork. It was mapped by careful surveys and patient counting. Astronomers measured the positions of galaxies and found that the universe looks like a web. One of the most influential projects for this mapping has been the Sloan Digital Sky Survey, which created massive three-dimensional maps of galaxies by measuring their redshifts and positions. Those maps reveal the cosmic web in a way that feels almost biological, as if the universe grew a skeleton made of galaxy clusters and filaments. And within that skeleton, voids are the spaces between ribs. There is a particular calm to voids because they highlight something easy to forget. The universe is not uniformly filled. It is clumped. Matter has preferences shaped by gravity, dark matter, and the early conditions after the Big Bang. The distribution is uneven, and that unevenness is not a flaw. It is a record of history. Voids are also useful. Their very emptiness makes them sensitive probes of cosmological models. When matter is sparse, small influences can be easier to detect. The expansion of the universe, the effects of dark energy, and the growth of structure over time all leave traces in how voids form and evolve. Even so, if you imagine drifting through a void, nothing about it becomes audible. There is no gas thick enough to carry a sound wave across those distances. The silence is not just the local silence of a spacecraft outside its hull. It is the silence of a region where even atoms are rare visitors. And yet, a void is not inert. It is part of a dynamic universe. It expands with cosmic expansion. It reshapes subtly as gravity pulls matter toward filaments. It is influenced by dark matter, which does not emit light, but does provide gravitational scaffolding. The void may look like nothing, but it is still inside the universe's rules. This is where the quiet begins to feel less like an absence and more like a message. The universe is telling you, gently, that sound is not the default. Sound is a special case, a local luxury, a phenomenon that requires density and intimacy. The cosmos as a whole is built for distance. And then, just as that thought settles in, the mind runs into a curious twist. Because if you spend time around astronomy, you may hear people say something that sounds almost contradictory. Sometimes scientists talk about the universe having a kind of sound. Not the kind you could hear with ears floating in space, of course, but something that still gets described with the language of acoustics. The phrase can sound poetic, even misleading, until the underlying idea becomes clear. The key is that sound is a wave, and waves come in many forms. In the early universe, long before there were stars or planets or galaxies, the universe was filled with a hot, dense mixture of particles. Not air, not water, but a plasma of photons, electrons, and atomic nuclei. In that environment, matter was close enough together to behave like a fluid. Pressure could build. Compression could spread. Waves could move through the primordial plasma. And those waves were, in a real physical sense, acoustic waves, pressure waves, sound waves. Not sound as a musical experience, but sound as a mechanical disturbance moving through a medium. These early pressure waves are connected to a concept called baryon acoustic oscillations. The words sound complicated, but the idea is surprisingly gentle when unfolded slowly. In the early universe, regions that were slightly denser than average pulled matter inward through gravity. But because the plasma was hot, it also had strong pressure pushing outward. That tug of war between gravity and pressure created ripples, waves of compression moving outward from dense regions like expanding rings in a pond. This process did not happen in silence in the physical sense, because the universe at that time was not empty. It was dense enough for pressure waves to propagate. Over time, the universe expanded and cooled. Eventually, it cooled enough for electrons to combine with nuclei to form neutral atoms. This epoch is called recombination. When neutral atoms formed, photons could finally travel freely without constantly scattering off charged particles. Light that had been trapped in the plasma suddenly had room to move. That released light is still traveling today. It has been stretched by cosmic expansion until it sits mostly in the microwave part of the electromagnetic spectrum. It is known as the cosmic microwave background. This cosmic microwave background was discovered in the 1960s by Arno Penzias and Robert Wilson, who detected a persistent background hiss in radio measurements. They were not looking for the origin of the universe. They were trying to solve a noise problem, but the noise turned out to be one of the most important observations in modern cosmology. Later missions studied this background in exquisite detail. NASA's Wilkinson Microwave Anisotropy Probe, often called WMAP, mapped tiny variations in that ancient light. The European Space Agency's Planck mission refined those measurements even further, revealing a detailed pattern of slight temperature differences across the sky. Those tiny variations are not random. They contain the imprint of the early universe's pressure waves. They are, in a sense, frozen echoes of those primordial acoustic oscillations. This is one of the strangest things about the universe. The cosmos is silent today in the ordinary sense because it is so thin. But the universe still carries a record of a time when it was dense enough for pressure waves to move through it. The silence now contains a memory of an earlier medium. There is another layer to the story. Those early pressure waves left not only a pattern in the cosmic microwave background, but also a preferred scale in the distribution of galaxies. The ripples set a characteristic distance, sometimes called the sound horizon, which later influenced how matter clumped into the structures seen today. When astronomers map galaxies across large volumes, they can detect this imprint statistically as a slight preference for galaxies to be separated by that characteristic scale. Surveys such as the Sloan Digital Sky Survey have been used to detect baryon acoustic oscillations in the distribution of galaxies, turning the universe itself into a kind of cosmic ruler. This helps measure how the universe has expanded over time, providing constraints on dark energy and cosmological parameters. Now, none of this means you could drift through space and hear ancient music. The universe is not broadcasting audible sound through the vacuum. What it means is that the physics of waves, pressure, and compression applied in the early universe, and traces of that wave behavior remain imprinted in light and structure. Sometimes, for outreach and education, researchers take astronomical data and translate it into sound for human hearing. This is called sonification. NASA and other organizations have released sonified datasets where, for example, changes in brightness become changes in pitch, or spatial patterns become musical patterns. This does not create a literal recording of sound traveling through space. It is a translation, a way of letting human ears perceive patterns that are otherwise visual or mathematical. That distinction matters. The universe is not suddenly becoming loud. The universe is being interpreted. And even that interpretation points back to the same quiet truth. Space is quiet because sound requires a medium, and most of the universe does not provide one. When scientists speak about cosmic sound, they are either describing early universe pressure waves that occurred when the cosmos was dense, or they are translating patterns into audio so human senses can grasp them in a new way. So the silence remains honest. It is the silence of emptiness, of separation, of distance. But it is not the silence of ignorance. The universe leaves evidence everywhere, and careful observation can recover stories older than any planet. In that sense, the quiet becomes almost reassuring. It is not a blank, it is a vast page, and the ink is written in light, motion, and faint patterns that began when the universe was young enough to carry waves through itself. And as you sit with that idea, the question changes shape slightly. It becomes less about why the universe is quiet and more about what quiet truly means, when the thing listening is a human mind built for air, for closeness, for crowded rooms, trying to understand a cosmos built on the patience of distance. By now, the pattern is starting to feel almost obvious. Sound thrives where matter is close together, and it fails where matter becomes sparse. But it is worth slowing down and looking at the mechanics a little more carefully, because the details explain something important. Sound does not merely prefer dense environments. Sound is built from density and pressure in the first place. On Earth, air pressure is easy to ignore because it is constant. It does not announce itself. It simply exists, pressing gently on everything, including you, including the walls around you, including the tiny hairs inside the ear that turn vibrations into perception. Pressure in this context is not a mysterious force. It is the result of countless air molecules colliding with surfaces every moment. Each collision is small, but together they add up to a steady push. Sound is a temporary disturbance in that steady push. When a sound source moves, it creates alternating regions of slightly higher pressure and slightly lower pressure. The higher pressure region is a compression, where particles are nudged closer together. The lower pressure region is a rarefaction, where they are spread slightly farther apart. These compressions and rarefactions travel outward, and the key word is travel. They move because particles are close enough to influence one another quickly, passing the disturbance along like a shared message. That message depends on two things that tend to travel together on Earth: density and pressure. A denser medium, in general, provides more particles per volume, which means more opportunities for interaction. A medium under higher pressure also tends to have particles closer together, making the chain of collisions more continuous. This is not a perfect one-to-one rule across all materials, but the basic intuition holds. Sound needs a medium that behaves like a connected community rather than a scattering of strangers. This is why sound behaves so differently in different substances. In solids, particles are bound tightly. Push on one part, and the disturbance spreads rapidly through the structure. That is why sound often travels faster through metal or rock than through air. In liquids, particles are close, though not locked in place. Sound can move efficiently there as well, which is why marine animals can communicate across large distances underwater in ways that would surprise most land creatures. In gases, particles are farther apart, and sound still travels, but less efficiently. It remains possible because, at Earth-like densities, collisions happen constantly. The pressure field is continuous enough to support a coherent wave. Now, remove most of the gas. Do not remove all of it, just most. The pressure drops, density drops, collisions become rare, the continuity breaks. A compression does not pass smoothly to the next region because there is no next region in the same connected sense. There are only isolated particles on long, lonely trajectories. In that situation, sound is not merely quiet, it is physically unformed. One way to feel this is to think about how sound behaves when conditions change, even slightly, on Earth. High-altitude environments can make voices carry differently. Thin air can reduce how sound propagates. In extreme laboratory vacuums, a ringing object can vibrate intensely while the surrounding space remains effectively silent. The vibration is real, but without a medium, it cannot become a traveling pressure wave that another listener can receive. This is also where the idea of absorption gets clarified. In many everyday situations, sound gets quieter because it is absorbed by materials or dissipated through friction. A carpet absorbs sound. Soft furnishings reduce echoes. Fog can dampen certain frequencies. These are changes within a medium. Space is not primarily a dampening medium. It is mostly a non-medium. Sound does not get absorbed by space the way it might be absorbed by curtains. The sound wave cannot form a stable traveling pattern because the environment cannot support the chain of compressions and rarefactions. It is not muffled. It is prevented. There is a quiet elegance to this. The silence of space is not an additional rule. It is the simplest consequence of the rules that already exist. This is where classical physics offers a useful anchor. Isaac Newton, in his broader work on motion and mechanics, helped establish that physical phenomena should be explained through forces and interactions rather than through vague qualities. Sound, when understood as a mechanical wave, fits that worldview neatly. It is motion distributed through a medium. It depends on the properties of that medium, including its density and its elasticity, meaning how it responds to compression. That elasticity matters. A sound wave is a tug of war between compression and restoration. A region of higher pressure pushes outward, and the medium resists being compressed, pushing back toward equilibrium. The interplay allows a wave to propagate. Without enough particles to push and pull in a coordinated way, that interplay collapses. This is why, when the density drops far enough, the very idea of a pressure wave becomes vague. Pressure itself becomes a statistical concept, meaningful over large numbers of particles. In extremely sparse environments, pressure is no longer something that can vary smoothly from point to point. It becomes a set of rare collisions that happen here and there. The medium is too grainy, too discontinuous to behave like a fluid for sound. At this point, the silence is no longer mysterious. It is the direct result of how sound is built. Sound is not a message that can cross a void. It is a pattern that exists only where matter is abundant enough to share the pattern. And yet, something else becomes even more striking. If sound fails in a vacuum, why does anything else travel so easily? Why can sunlight cross the solar system without trouble? Why can radio signals from a distant spacecraft reach Earth from beyond the realm of planets? Why can the ancient glow of the cosmic microwave background cross billions of light years of expanding space and still arrive as measurable radiation? The answer is that sound is one kind of wave, but not the only kind. Sound is mechanical. It is built from matter bumping into matter. But light is electromagnetic. It is built from changing electric and magnetic fields that can sustain one another and propagate through space without needing a material medium the way sound does. This distinction was not always obvious. For centuries, people debated the nature of light. Some imagined it as particles, others as waves. When waves were considered, many assumed waves required a medium, as sound waves do, leading to the idea of a universal substance sometimes called the luminiferous ether. The story is long and winding, but the important result is beautifully simple. Light does not require such a medium in the way sound does. A major step toward that understanding came through the work of James Clerk Maxwell, who unified electricity and magnetism into a single framework. In that framework, changing electric fields generate magnetic fields, and changing magnetic fields generate electric fields. The interplay allows electromagnetic waves to propagate, carrying energy and information through space. Unlike sound, an electromagnetic wave does not need a crowd of particles to pass a vibration along. It is not a pressure change moving through matter. It is a self-sustaining disturbance in the electromagnetic field itself. This is why space, though silent, is not blank. The universe is filled with light across a vast range of wavelengths, from radio waves to microwaves to infrared, visible light, ultraviolet, X-rays, and gamma rays. These are all forms of electromagnetic radiation. They travel through vacuum readily, and in many cases, vacuum is the best environment for them because there is little to scatter or absorb them. On Earth, sunlight is filtered by the atmosphere. That filtering is life-saving, especially for high-energy ultraviolet radiation that can damage biological tissue. But it also means Earth is a complicated place for observing the full electromagnetic spectrum. That is one reason space telescopes exist. By placing observatories above the atmosphere, organizations such as NASA and the European Space Agency can observe the universe in wavelengths that would otherwise be blocked or distorted. This is where the silence of space becomes almost practical. Space is quiet to the ear, but it is transparent to many forms of electromagnetic information. That transparency is one of the reasons astronomy is so powerful. It turns the universe into a long-distance messenger system. Stars communicate primarily through light. A star's temperature, composition, and motion can be inferred from its spectrum, the way its light is spread across wavelengths. Elements such as hydrogen, helium, sodium, calcium, oxygen, and iron leave characteristic absorption lines in starlight. Astronomers use these signatures to determine what stars are made of, how hot they are, and how they move relative to Earth through a process called the Doppler effect, which shifts wavelengths depending on motion. This is not sound, but it is information. Planets can be detected through their gravitational influence on their host stars, and through the subtle dimming of starlight when they pass in front. An approach used by missions such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey satellite. Again, no sound is required. The universe gives evidence quietly, and instruments learn to read it. Even phenomena that seem violent and energetic express themselves through electromagnetic signals. Supernova remnants glow in X-rays. Pulsars flash in radio waves. Black hole accretion disks radiate strongly in X-rays and ultraviolet light. Jets from active galactic nuclei shine across multiple wavelengths. The energy is real and the motion is dramatic, but it is not audible. It is visible in the language of electromagnetic radiation. And this is where the question of silence becomes something richer than a simple absence. Space is quiet because sound is mechanical and requires density. But space is also loud in another sense, filled with electromagnetic activity that would overwhelm human senses if it could be experienced directly without filtering. If the human ear could somehow detect radio waves the way it detects pressure waves, the universe would not feel silent at all. It would feel crowded with signals. But ears were not built for that. They evolved to interpret vibrations in air because air was the medium life grew up inside. So the silence of space is partly a truth about physics and partly a truth about biology. The human body is tuned to one kind of wave in one kind of environment. The universe is dominated by other waves in other environments. This also explains a common point of confusion. When people hear that astronomers have translated cosmic data into sound, it can sound like someone has recorded the universe. But what is happening is a conversion. Data that exists as light intensity, frequency, or timing is mapped into audible frequencies so the human ear can detect patterns. This is useful, and it can be beautiful, but it is not the same as sound traveling through space. The cosmos does not carry pressure waves across the vacuum the way it carries light. What it carries, relentlessly and elegantly, is electromagnetic information. And once that distinction settles in, the silence becomes less haunting and more instructive. It tells you what kind of place you are in. It tells you that matter is sparse here. It tells you that vibration cannot travel by contact, because contact is rare. But it also tells you that the universe is not withholding itself. It is offering itself in other forms, in photons that cross ancient distances, in radio waves that slip through darkness, in infrared heat that reveals cold dust clouds and star-forming regions. So the quiet of space is not a lack of communication. It is a shift in language. Sound is the language of crowded matter. Light is the language of the vacuum. And in the long night of the universe, it is light in all its forms that carries the story forward. And once the idea of language settles in, it becomes tempting to ask a very human follow-up question. If space itself cannot carry sound, can space ever be loud at all? The honest answer is yes, but only in places where space stops behaving like empty space and starts behaving like a medium again. Loudness is not a property of drama. It is a property of density, pressure, and contact. Inside a thick atmosphere, sound is perfectly at home. On Earth, it is everywhere. On Titan, Saturn's largest moon, there is a dense nitrogen atmosphere, and sound would travel there in ways that would feel familiar, though the details would change with the different temperature and composition. On Venus, the atmosphere is even denser, and it presses down with a force that makes the idea of an unprotected human standing there almost unimaginable. In an atmosphere like that, sound would propagate strongly because the particles are packed tightly, and pressure waves would have an easy time moving through the gas. Jupiter and Saturn are different again. They are not solid surfaces with atmospheres above them in the same sense. They are giant balls of gas and fluid with immense pressure deep inside. In their upper layers, winds can reach extraordinary speeds. Those winds would generate turbulence, and turbulence in a dense gas creates sound. The storm systems on Jupiter, including the Great Red Spot, are driven by fluid motion and energy transfer on a scale that dwarfs anything on Earth. If a listener could safely float within those layers, there would likely be a constant roar of motion, a deep, restless soundscape shaped by wind shear, convection, and waves moving through the gas. Mars is a quieter example, and it is a useful one because it shows that sound is not just present or absent, but shaped by environment. Mars has a thin atmosphere, mostly carbon dioxide, with much lower pressure than Earth. Sound still exists there, but it behaves differently. NASA's Perseverance rover has recorded audio on Mars. demonstrating that sound can travel in the Martian air, though it is fainter and more altered than it would be on Earth. The point is not that Mars is loud. The point is that Mars has enough atmosphere for sound to exist at all, even if it is a fragile version of the thing your ears are used to. The deeper you go, the more the universe offers local pockets where sound can exist. Not out in open vacuum, but inside dense places. A star, for example, is not just a bright object. It is a dynamic body of plasma, dense enough in many regions to support waves and oscillations. The sun is a perfect example because it looks calm from a distance, yet it is constantly in motion. It convects, it boils. Hot plasma rises, cools, and sinks. Magnetic fields twist and reconnect, releasing energy in flares and shaping sunspots. Within that churning material, pressure waves can travel. Scientists study these waves through a field called helioseismology. The name sounds like it belongs to earthquakes, and in a way, it does. Seismology studies waves traveling through a body, revealing its inner structure. Helioseismology uses oscillations on the sun's surface to infer what is happening inside it. By observing subtle motions and patterns, researchers can map how the sun rotates at different depths and latitudes, and can learn about its internal layers. This is one of the most quietly astonishing things in astronomy. The sun has a kind of internal ringing. It vibrates in many modes at once, and those vibrations contain information about regions no instrument can directly see. It is not sound that travels through the vacuum to Earth. It is sound in the physical sense of pressure waves moving through a medium, and those waves are detected indirectly through motion and light. There is a similar idea in astroseismology, which applies to other stars. The details vary, but the principle is the same. Dense stellar material can carry waves, and those waves can, in some cases, be inferred from the star's brightness variations and surface motion. Stars, in that sense, are not silent internally. They are full of physical oscillations. Planets can have their own versions of this too. Earthquakes are pressure waves traveling through solid rock. On the Moon, impacts and tectonic events can create moonquakes that send vibrations through lunar material. Those vibrations can persist for a long time, partly because the Moon is dry and lacks the kind of water and fractured rock that damp vibrations quickly on Earth. Again, none of this becomes audible in the space above the surface, but it is sound in the physical sense, living inside matter. Even gas clouds can support local waves if they are dense enough. In certain nebulae, shock fronts from supernova remnants push through gas, compressing it. Within that gas, pressure differences and turbulence can create wave behavior. The universe is full of these local environments, but they are islands. They do not connect into a universal ocean of sound because between them lies vacuum. So if the question is whether the universe contains loud events, the answer is yes. In the right medium, the physics of sound applies. But if the question is whether there is a universal soundtrack floating through space, the answer remains no. Loudness does not travel through emptiness. It must be hosted. This is where it helps to separate two instincts that often blend together in the imagination. One instinct says that great energy should make great sound. The other says that great motion should make great noise. On Earth, those instincts are often correct, because air is always present to convert energy and motion into pressure waves. But the universe does not owe that conversion to anyone. Energy can exist as radiation, as particle motion, as magnetic fields, as heat, as gravitational potential, and it can remain silent to the ear the entire time. A supernova is a perfect example. The explosion involves shock waves, turbulence, and violent compression inside the star's outer layers and the expanding debris. There is, in the physical sense, a roaring storm of pressure and motion within that material. But outside that material, the vacuum waits. The shock front expands into a medium that is too thin to host it as sound in the way a planet's atmosphere would. The event is not quiet because it is gentle. It is quiet because it is not happening inside air. Even closer to home, a rocket launch is thunderous at sea level because it is pushing against dense atmosphere and creating enormous pressure waves. The same rocket, once it climbs into thin air and then into space, becomes visually dramatic but acoustically irrelevant to the surrounding vacuum. The loudness is an Earth phenomenon, not a universal one. And there is a small, dry humour hidden in that. Humanity's loudest machines, the ones built to escape Earth, lose their voice the moment they succeed. They still burn and thrust and accelerate, but they do it in a silence so complete that the only way to experience it is through instruments and imagination. So yes, the universe can be loud, but loudness is local. It lives in atmospheres, in oceans, in rock, in plasma, in clouds, where particles are close enough to push and pull on each other. Open space between those places stays silent, not because nothing happens there, but because contact is rare. And once that is understood, another question begins to rise more softly. Why does the silence feel the way it feels? The physics is clear, but the emotional response can be surprisingly strong. Silence in space can feel peaceful, frightening, holy, indifferent, or unbearably empty, depending on the listener and the moment. That reaction is not just philosophy, it is biology. Human hearing evolved for a world where sound is a survival tool. Ears are built to detect vibration in air, and the brain is built to treat sound as information about nearby events. A sudden noise might mean danger. A familiar voice might mean safety. A subtle change in a soundscape might mean something is approaching, something is leaving, something has shifted. In that context, silence is not neutral. Silence can mean that information is missing. The auditory system is always working, even when you are not paying attention. It filters, prioritizes, and highlights. It turns pressure waves into neural signals and then into meaning. And the brain does not merely register sounds, it predicts them. It carries models of what should be heard in a given environment, and it compares incoming signals to those expectations. When the brain expects sound and receives none, it does not simply relax. Sometimes it becomes more alert. This is why a sudden drop in background noise can feel unnerving. In many environments on Earth, a quieting of the soundscape can indicate a change that matters. Even animals respond to this. A forest can become quiet when a predator appears, and the absence of usual noise becomes its own signal. Neuroscience has a name for some of this predictive behavior. Predictive processing is the idea that the brain continuously generates expectations and updates them based on sensory input. Auditory perception is deeply tied to that. The brain is not a passive microphone. It is an active interpreter. This helps explain why the silence of space feels uncanny. It is not simply quiet like a calm room. It is a kind of quiet that removes a major channel of environmental feedback. A listener might imagine floating outside a spacecraft and instinctively wait for cues that will never arrive. No wind, no distant rumble, no subtle acoustic reassurance that the world is nearby and responsive. Even the body's relationship with vibration changes. On Earth, low-frequency sound can be felt in the chest. Loud sounds can be felt in the skin. Vibrations travel through floors and furniture. In a vacuum, those sensations vanish unless you are physically touching a vibrating object. The absence of those cues can make the environment feel less real, as if the universe has been muted. There is also a psychological layer. Humans often associate silence with vastness. A large, empty building can feel eerie, partly because sound behaves differently inside it. Echoes stretch, footsteps become pronounced. The auditory system registers scale through reverberation and reflection. In open space, there are no reflections. There is no reverberation. There is only nothing returning. The brain reads that as a kind of infinity, and the mind, being the mind, tends to attach meaning to infinity. Sometimes that meaning is wonder. Sometimes it is unease. Sometimes it is both at once. This is also why the fiction of sound in space can feel emotionally satisfying. Films and stories use sound to provide a sense of impact and closeness. A roaring engine makes a spacecraft feel present and powerful. A booming explosion makes an event feel immediate. These sounds act like a bridge between the viewer and the scene. They make the environment feel like Earth, even when it is not. Real space removes the bridge. That removal can be calming when approached slowly. It can feel like the ultimate quiet room, a place where the world's noise finally cannot follow. But it can also feel like isolation because the brain equates silence with absence of nearby life. In everyday experience, a completely silent environment is rare. Even at night, there's usually wind, distant traffic, the subtle creak of buildings, the movement of air through vents. The human nervous system is used to a constant acoustic baseline. Space offers none. There is another subtle effect as well. When auditory input drops, the brain sometimes fills in gaps. In quiet environments, people can become more aware of internal sounds, such as heartbeat, breathing, or the faint ringing that many people experience, known as tinnitus. The quiet does not create these sensations, but it removes competition. It gives them room. In that way, silence can feel louder than expected, not because the environment is noisy, but because attention turns inward. This makes the silence of space a mirror. Without external sound, the mind hears itself more clearly. And perhaps that is why the question matters for a late-night channel like this. The physics explains why space is quiet, but the experience of the quiet explains why the idea stays with people. The universe is vast and indifferent to human senses, and yet human senses are the only way the universe becomes emotionally real. So the silence is two things at once. It is a simple physical consequence of low density, and it is a psychological boundary, the place where a sense evolved for air meets a cosmos built on distance. Once those two layers are held together, the quiet becomes less like a horror and more like a truth you can rest inside. It does not need to be filled with noise to be alive with meaning. It is enough to understand what the silence is, what it is not, and why the human mind reacts to it so strongly. And from here, a final shift begins to form. If silence can feel unsettling, maybe it can also be useful. Maybe quiet is not just what happens when sound disappears, but something science can work with, something that allows detection, measurement, and precision in a universe that speaks most clearly when it is not competing with its own noise. There is a strange comfort in realizing that silence can be practical. On Earth, noise is often treated as a byproduct of activity. Engines roar, crowds rumble, storms howl, and machinery rattles because energy is being lost in messy ways. Friction, turbulence, collisions, and uneven surfaces all turn motion into sound. A loud environment is often an environment where energy is being scattered into the air. Space does not scatter energy into air because there is no air to take it. That means the silence is not just a feeling. It is a condition that changes what can be measured. In a quiet environment, small signals stand out. In astronomy and space science, much of the work is exactly that. Noticing the faint thing hidden inside the bright thing. Detecting a slight wobble in a star that suggests a planet. Seeing a weak shift in a spectral line that reveals chemical composition. Measuring a delicate distortion in space-time itself. This kind of science depends on sensitivity, and sensitivity depends on reducing interference. On Earth, interference is everywhere. The atmosphere blurs and scatters light. Weather changes transparency. Temperature shifts distort telescopes. Vibrations from traffic can shake instruments. Human activity fills the environment with radio signals. Even the ground itself is restless, constantly trembling with ocean waves, wind, and the slow movement of tectonic plates. That restlessness does not make Earth a bad place for science. It makes Earth a complicated place for science. Many of the greatest experiments in history were done here, and the ingenuity required is part of the story. But it also means that when scientists want to detect the faintest signals, they often go where the environment is quieter in the ways that matter. Space, in many respects, is quieter. Not acoustically, because that is already settled, but in terms of certain kinds of interference. There is no atmosphere to blur starlight. There is no weather. There is no wind buffeting a mirror. A space telescope can stare for hours without the sky brightness of Earth interfering, and can detect faint objects that would be swallowed by atmospheric glow on the ground. This is one reason the Hubble Space Telescope became so transformational. It is not that Earth-based telescopes are weak. Many ground observatories are larger and more powerful in raw collecting area, but Hubble's position above the atmosphere gave it a clarity that changed what humans could see. The James Webb Space Telescope extends this idea further, observing in infrared wavelengths where the cold, faint glow of distant galaxies and dust clouds can reveal features invisible to other instruments. The silence also matters for radio astronomy. On Earth, radio telescopes deal with constant interference from human technology. Communications networks, satellites, radar systems, and countless electronics leak radio emissions. Engineers and astronomers work hard to isolate true cosmic signals from the noise of civilization. That is one reason some radio observatories are built in remote locations and protected by radio quiet zones. In space, radio interference can still exist, especially near Earth, but the environment can be far cleaner depending on location. The far side of the Moon has been proposed as an ideal place for certain kinds of radio astronomy, because the Moon itself blocks much of Earth's radio chatter. This idea is not science fiction. It is a practical proposal shaped by the value of quiet, not for ears, but for detectors. Silence as information goes even deeper than that. In science, what is not happening can be as important as what is happening. When astronomers look at light from a distant star and see missing wavelengths, that absence reveals the presence of certain elements absorbing specific energies. When a cosmic ray detector registers a drop in particle flux, that drop can indicate a change in the space environment or the influence of magnetic fields. When the cosmic microwave background shows tiny cold spots and warm spots, those small differences, those slight deviations, become clues to the early universe. In this sense, quiet is not nothing. Quiet is contrast, and contrast is how measurement works. This is where one of the most striking examples can enter calmly, without spectacle, because the facts are already astonishing enough. There is an experiment that is, in a way, a kind of listening, not to sound, but to the universe, flexing. The laser interferometer, gravitational wave observatory known as LIGO, is designed to detect gravitational waves, ripples in space-time predicted by Albert Einstein's general theory of relativity. These waves are not sound waves. They do not move through air. They are changes in the geometry of space-time itself, produced by accelerating masses, especially enormous masses in violent motion, such as merging black holes or neutron stars. LIGO detects these waves not by hearing them, but by measuring tiny changes in distance along long arms using laser light. The changes are extraordinarily small, far smaller than the width of an atom. Detecting them requires extreme isolation from noise. The facilities use sophisticated vibration control, vacuum systems, and careful calibration to separate genuine cosmic signals from local disturbances. When LIGO made its first direct detection of gravitational waves in the 2010s, it opened a new way of studying the universe. It was not a new kind of sound, but it was often translated into audio form for public understanding. The signal can be mapped into a rising tone, sometimes described as a chirp because the frequency increases as two objects spiral together faster and faster before merging. That translation is not a literal recording of sound traveling through space. It is a representation, but it captures something emotionally true. The universe has rhythms, it has patterns, it has events that unfold like waves, even when no air exists to carry a noise. The quietness of space, the absence of ordinary sound, is part of what makes these delicate detections possible. A universe filled with thick atmosphere would be a universe filled with turbulence and friction. It would be a different universe, harder to observe at long distances. The vacuum is not just an emptiness, it is a clarity. Even in particle physics and space instrumentation, vacuum is used as a tool. Spacecraft instruments often operate in vacuum conditions by necessity, but also by design. Detectors for ultraviolet and X-rays rely on low interference environments. Sensitive thermal measurements require isolation. Many instruments would not function properly in dense air. So silence becomes a kind of enabling condition, not for ears, but for knowledge. Once that idea has settled, it becomes easier to hold the biggest truth of the whole topic. Space is quiet, yes, but it is never still. A quiet universe is not a paused universe. Start with the solar system. Earth is moving around the sun at tens of kilometers per second. The moon is orbiting Earth. Planets sweep through their paths in immense arcs. Comets fall inward and swing out again. Asteroids tumble and drift. The sun itself is moving through the Milky Way. The Milky Way is rotating. The local group of galaxies is moving through the expanding universe. All of this motion happens in near silence because motion does not require sound. Sound is not the signature of movement. It is the signature of movement interacting with dense matter. This distinction is almost philosophical, but it is also strictly physical. A vacuum allows motion to persist with very little friction. On Earth, if you slide something across a table, it slows. If you throw a ball, air resistance and gravity shape its path. Energy is constantly being converted into heat and sound. In space, objects can coast for long periods because there is little to slow them down. This is why orbits are possible in the stable way they are. It is why a spacecraft can travel vast distances using relatively small thrust compared to what would be required to fight through thick air. The quiet in that sense is the sound of efficiency. It is the sound of friction being absent. Yet the universe is not frictionless everywhere. Gas clouds collide, plasma interacts through magnetic fields, stars lose mass through stellar winds, supernova remnants expand into surrounding material. Galaxies merge and tear at each other gravitationally. Even in deep voids, the expansion of the universe continues, stretching space itself. The expansion is one of the most profound forms of motion. Galaxies beyond the local group are, on average, moving away, not because they are flying through space like bullets, but because space between them is expanding. This is connected to modern cosmology and observations that began with Edwin Hubble, who found that more distant galaxies tend to have higher redshifts, indicating they are receding. Later work revealed that the expansion appears to be accelerating, a discovery linked to observations of Type I as supernovae and associated with the concept of dark energy. None of this is audible, yet it is among the most important motions in the universe. So the quiet becomes a kind of honest indicator. It tells you the universe is not filled with a medium like air. It tells you distances are enormous and matter is sparse. It tells you that many processes unfold without friction. But it does not tell you that nothing is happening. It tells you that what is happening on scales where your senses were never designed to follow without help. In this way, the silence becomes a form of truth. It strips away the idea that activity must announce itself. It removes the emotional comfort of a soundtrack. It forces a clearer understanding of cause and effect. Dense matter produces audible waves. Sparse matter does not. Motion can be enormous and still be quiet. And when that is fully absorbed, the quiet stops being a threat. It becomes a kind of perspective. The universe does not need to shout to be real. It does not need to roar to be powerful. It can do extraordinary things in absolute silence, and those things can still be known, measured, and understood. The silence is not the universe hiding. It is the universe being exactly what it is: vast, dilute, and endlessly in motion. Now the question has an answer that feels almost too simple for how haunting it can be. Space is quiet because sound needs a medium, and most of the universe does not provide one. Sound is a pressure wave. It is matter pressing into matter, passing a ripple along through contact. On Earth, that contact is everywhere, so sound feels like a basic feature of reality. But the moment you leave the thick air near the surface, the crowd of particles thins. The chain breaks. the ripple stops being a ripple. Silence, then, is not evidence that nothing is happening. It is evidence that things are happening far apart. Between planets, the solar wind streams outward in silence. Between stars, the interstellar medium drifts so thinly that even atoms are rare companions. Between galaxies, cosmic voids stretch wider than any human story, and the quiet becomes less like a lack and more like a measure of scale. And yet, the universe is never still. Stars burn with nuclear fusion, galaxies rotate, supernova remnants expand, black holes gather matter and fling energy outward in jets. The universe itself expands, stretching space between distant galaxies. None of this needs sound. None of it is diminished by silence. Motion does not require an audience. The quiet also does not mean the universe is unreachable. Space speaks constantly through light, through radio waves, through infrared warmth, through X-rays and gamma rays, through patterns in the cosmic microwave background, through gravitational waves detected by observatories such as LIGO. The cosmos communicates, but not in the language human ears evolved to understand. So the silence becomes a kind of honesty. It tells you what the universe is made of and what it is not. It tells you that the cosmos is dilute, vast, and patient. It tells you that sound is local, intimate, and dependent on closeness, while most of reality is defined by distance. And perhaps that is the calmest thought to carry into the night. Somewhere above every roof and cloud, beyond the last thinning trace of air, there is a place where nothing echoes. Not because the universe is empty, but because it is wide. Not because it is dead, but because it is spread out into a scale that does not need noise to exist. If you are listening from a quiet room, a late shift, a soft corner of a long night, that silence around you is not so different from the silence out there. Both are spaces where the world steps back a little, and the mind can notice what it usually rushes past. And when the thought arrives that the universe is quiet, it no longer has to feel unsettling. It can feel like permission. Permission to let the noise go. Permission to sit with the fact that reality does not always announce itself. And permission to rest while the stars keep moving in their own calm, soundless way.